The first thing we talk about is roots. So far, we have done a ton with square roots, right? I mean, quadratic formula has square root. By square root, they mean an index of 2, or that you are taking the root when something multiplies twice to get to it. Like in our bell work, 5 times 5 is 25. That is the square root, meaning you are looking for something that pairs up in 2s, right? You can have different roots. We actually did it with the cubed difference of cubes, right? You had to look for a cubed root, which means the third root of it. So they gave 5 as an example. 5 squared is 25. Still, so 5 squared is 25. So 5 is considered the square root of 25. 5 cubed is 125. So 5 is the cubed root. You see, we just have this fourth root, fifth root. So this pattern gives us what's called the nth root. You can have any root that you want. You're just saying how many times does it multiply to get to this number. For any real number a and b and any positive integer n, if a to the nth equals b, then a is the nth root of b, all right? And so they're just saying you can have, any number of roots actually that you can find for a number. So let's talk about what does that do? The cubed root. So we are looking for something that multiplies 3 times to get to these numbers. Well, if I want something that multiplies 3 times, I am going to look at a couple things. Decimals, so you have to count the decimals, okay? So I have 3 decimal places. You have to keep in mind what happens when you multiply decimals. Well, you add up all the decimals. Remember from way back when we started multiplying decimals, probably in elementary school sometime. If you multiply decimals, you multiply the numbers just the way they are. You count up how many decimals you started with. Your answer has that many decimals in it, okay? So if I'm looking for the cubed root and I have 3 decimal places, the answer to what I'm looking for is going to have 1 decimal place. That's how it works. So I just have to worry about the cubed root of 8. What is the cubed root of 8? 2. So then the cubed root of 0.008 is going to be 0.2. All right? When you look at something like this, negative 1,000, because it is a negative, that's okay as long as it is a cubed root, because 3 negatives are possible to multiply and get a negative. When you have something with zeros, a good rule of thumb is look at my zeros, all right? I have 3 zeros here, all right? So I'm going to multiply something with 1 0 each, because that's how multiplication works with zeros. So the cubed root of something like negative 1,000 is going to be negative 10. Follows that pattern. Square roots can only be positive because 2 negatives make a positive, so you can't have a negative in the root. But you can have a negative in a cubed root or a fifth root or any odd root, because you can multiply 10 3 times if it is negative and get a negative. When you are taking the roots of fractions, you take the root of the numerator and the root of the denominator separately, and then that's your answer. So for this guy right here, the third root of 1 is 1. The third root of 27 is 3. So my cubed root there is 1/3. All right. Questions on finding those. Fourth root works the same. I will say any root of 1 is 1. So 1 is a perfect everything. Perfect square, perfect cube, perfect to the fourth. Okay. So if you're looking for any root of 1, it is 1. So then this guy right here, they want the fourth root. With this one, we have a problem. Why can't I have the fourth root of this guy? It is a negative, and my root that I'm looking for is even, all right? Even roots have to be positive, all right? We're not talking about imaginary numbers right now. We're talking about real numbers. And so if it is a negative number in the real number world, cannot be an even root, because even roots are going to pair up. When negatives pair up, they are positive in multiplication, okay? So this has no real number, so no real number here. And then once again, fourth root, all right? I will say that for this last one, when you're doing the fourth root of a fraction, you're going to do it exactly the same, right? So fourth root of 16, fourth root of 81, if one of them doesn't have it, we'll deal with rationalizing those later. But you just have to do them individually. And it's possible that one of those could be something you just simplified the root. In this case, they gave us 2 that simplify to 2/3. But there are going to be times with fractions that you may have to leave a radical in your answer. And we'll talk about getting rid of those as we have done in the past. All right, questions on finding roots. Pretty straightforward. By the way, if you don't know what the root is, like say for some reason you didn't know the fourth root of 81, how would you go about finding it?
Just do the square root of 81 and the square root of that square root.
Right, so you're basically doing prime factorization, all right? Our lovely, lovely factor tree, right? So if we do something like this, if you know that's 9, if you're looking for the fourth root, 1, 2, 3, 4, there we go, it's going to be 3. So when in doubt, you can use your factor tree. You're looking for something that repeats whatever number of times it is telling you that it wants, all right? So if you don't know, if it's some large number, just do prime factorization and you will find it. All right, let's talk about some terminology. A radical sign is used to indicate a root. All right, so when I'm talking about the radical sign, I'm talking about this guy right here, all right? The index, it gives me which root I'm looking for. If you do not see an index, the assumed root is square root. So the assumed index here is 2, all right? Otherwise, it will tell you what root they're looking for. The radicand is the number inside here that you are taking the root of. When a number has 2 real roots, the positive root is called the principal root. So remember when we took, like, if you have a variable involved, the square root of 9, you would say positive or negative 3, okay? Unless a variable is involved. Like if I just say, if I give you a list of roots and I want the answer, and I say square root of 9, you're going to give me 3. That is the principal root, okay? If I say x squared equals 9, that is a different question than just me putting the square root of 9 on a test and you giving me the root. If it says x squared equals 9, then you are going to look for both the principal and the other root, the positive and negative root, okay? There is a difference when a variable is involved because I can plug it back in and get the answer. Now, if you are solving an equation and you plug your answer back in to check it, you have to assume principal root. Because when you are plugging something back in to check an answer, you are not solving at that point. You are simply doing order of operations. Think about when you solve an algebra problem. When you plug your numbers back in, there are no variables. You're plugging numbers back in to see if it works, and you strictly do PEMDAS to see if your answer gives you a true statement. So when you plug an answer back in, and it gives you maybe the square root of 9 equals negative 3, then that is not an answer because the square root of 9 in PEMDAS equals principal root 3. And so we will get to those examples when we do some solving. I just want to point that out, that we are typically looking for the principal root unless you are solving an equation with like an x squared. All right, so here's the property. For any negative real number a to the nth, so we have a to some power inside a radical, you are going to use an absolute value when n is even. Why do we do this? Okay. If you have an even root, so I am looking for an even index here, and I get some variable that comes out of it, because it was an even index, I have to indicate that guy is always going to be positive. Because again, I'm talking about the real number world, not the imaginary, okay? And so if I have an even root, then my answer that comes out of it, I have to assume is positive, or else someone could come along and plug in a negative side of that, and you would have a negative under your root when you plugged it back in. And so we're going to look at examples of that too. There are times when you need to use absolute value when you're solving these, or when you're giving the answer for them, because plugging it back in could cause a problem under the root. Let's look at these examples. Find each real number root. All right, so for this first one, it says in your instructions, real number. That tells me complex numbers are out, okay? I am looking for the cubed root of a negative number. No problem. What is the cubed root of negative 8? Negative 2. And we're done. However, on this guy, what is my index here since I don't have one? What's my index if I don't see one? 2. I'm going to assume it's a 2. This has no answer for real numbers. So this would be no real number.
So whoever does it, you just literally write no real number.
Mm-hmm. In the world of solving quadratics, you would write 10i, okay? But when I'm asking for a real number solution, it is no answer there. No solution to this if you're in the real numbers. Complex numbers, that's different. For these, we're talking about real numbers.
Are we going to do it where we have to do the 10?
Because if I were to do this, I can do negative 2 times negative 2 times negative 2, and that equals negative 8, because it is a odd. But for an even root, it's going to pair up, and it's going to turn positive. All right, so there's a couple ways to do variables. I'm going to show you my way. All right. So when you have a radical and it has numbers and variables, just do them individually. All right. Easy enough. I have, and all of these work out nicely, so we don't have to worry about them. Maybe they get a little more difficult later on. Square root. Square root of 4, that's easy. That's 2. For this guy, you're just going to take your exponent, that's 6, divide by your index. My index is a 2. So the x is going to come out as x to the third power. However, can x to the third power ever be negative? Can I choose a number for x that would make that a negative number? Yes? Yes. I could say -2, and that would be -8, like we just saw. So because I had an even index and my exponent came out to be odd, which would potentially give me a negative number, my even index requires a positive number, all right? So I have to do absolute value around this guy. I have to do absolute value because he could be negative, and my index tells me I can't have a negative in the root. All right? Had he been x to the 4th, it would be unnecessary to write because x to the 4th will never be negative. So I don't have to force it to be positive. It always is. But because x cubed can be negative and my index says I can't have a negative, I must put an absolute value there. Question. There. All right. So for this one, I don't have any numbers to worry about. So for my a, I would just say my exponent divided by my index. So I'm going to take the a out to the first power. For my b, I'm going to say my exponent divided by my index. So I'm going to take the b out to the second power. All right. A could be negative, correct? Because it's to the first power. Does it matter if a is negative? Well, it doesn't because this is a 3. So inside of that could be positive or negative. It doesn't matter. It's an odd index. So I do not require absolute values here. Not required because my index was odd. I can have positive or negative with an odd index. So with an odd index, you will never need an absolute value when you solve it, ever. The only time you have to decide if an absolute value is necessary is with an even index. All right, so for this one, my x is to the 4th power, so it's 4 divided by my exponent divided by my index is a 1. And for my y, it is an exponent of 8 divided by index 2. And so like this question before, it is an even index. I need to check my answer. My x is to the first power, which is potentially a negative number. So this guy requires absolute values. The y squared does not. If the y had been cubed there, I would just put absolute value around the entire thing.